All right. Boy, that last video was a doozy, wasn't it? Kind of abstract and weird and maybe confusing. If so, I think that this video will be a little bit easier for you to understand. We're just going to calculate some derivatives. So it's very calculative. We're just kind of simplifying things algebraically here. So once we do a couple examples, I don't think you'll be so scared of these derivatives, okay? So if you understood from the last video what a derivative is, and you understand what this function is, you might be confused why we're doing this problem where we're supposed to find the derivative of this function at the point x equals 5. Okay, so this function is a what? It's a line, right? mx plus b, the m is the slope. This thing has a slope of 2 and a y-intercept of -3. Let's just draw a quick little graph. My y-intercept at -3, 1, 2, 3, so I know I cross the y-axis there, and then I have a positive slope of 2, so something maybe like that. Right? So there's my line. I know the slope everywhere on my line is positive 2, right? So the derivative, or the slope of that tangent line that we looked at from the last video, is just going to be the same as the slope of the line everywhere, right? It's going to be a slope of positive 2, even at the point x equals 5, maybe over here. This point right here, the derivative is asking us, what's the slope of the tangent line at x equals 5? Well, it's going to be the same as the slope of the line at x equals 5. The slope is 2. Okay, so if you understand the calculus here, you understand that the answer to this problem is just 2, and we can move on. But I want to prove to you that our formula that we discovered in the last video actually works. This formula right here, the limit as h approaches 0 of f of x plus h minus f of x all over h. That formula for the derivative of a function works even for simple functions like a line where we already know the slope. So this is more of just an exercise. Okay, so in order to do this, I first need to calculate f of x and f of x plus h, and then we can start to simplify this. What's the problem with this right now? We kind of went over it in the last video. The problem is that h is approaching 0 and h is my denominator, right? And if I were to just have h be 0, we'd have an undefined expression here, right? So somehow I want to get h out of that denominator, right? So that we can get some sort of we want to get positive 2. Okay, so first we realize that, well, we're doing one x value, x equals 5, so I can just substitute 5 in for my x values. Okay, so first let's do these one at a time. Let's do f of x. Let's just find f of 5, right? Well, we know that we just substitute 5 in there, right? So that'd be 2 times 5 minus 3, 10 minus 3, that's 7. So that's what I'm going to substitute right there for f of x. Okay, and then we have f of x plus h, so that would be f of, well, I know x is 5, 5 plus, now what do I substitute in for h? I don't substitute anything in for h, okay, because h is my limit variable. We don't substitute anything for that, so I just leave that as 5 plus h. So I substitute 5 plus h in for x in my function. 2 times 5 plus h minus 3. We could simplify that. I could distribute the 2 in there. 10 plus 2h minus 3. And I could combine my 10 and my 3, and I'd get 7 plus 2h. So there is f of x. There is f of x plus h. Now I can substitute those in over here for f of x and f of x plus h, right? So my derivative becomes the limit as h approaches 0 of f of x plus h, which I know is 7 plus 2h, minus f of x, which I know is just 7, all over h. Remember, we don't substitute anything for h because that is our limit variable. Okay. All right, can we do anything here? Yeah, I can simplify my numerator. So that becomes the limit as h approaches 0 of, I have 7 minus 7, which is 0. So that just leaves me with 2h. 2h over h. Okay, now if I let h become 0 here, we still end up with 0 over 0. But algebraically, this expression, what happens? H divides by h, and we get 1. Right? And 2 times 1, well, this just becomes the limit as h approaches 0 of 2. Okay? Now, how do I deal with this limit notation over here? Once we have this boiled down to a constant, we don't have to worry about this. Because remember, what is this doing? This is saying that h, the variable h, if it were here, would be getting closer and closer to 0. Okay? Well, h isn't here anymore. So it doesn't matter what h is doing, because h does not affect 2 at all. As a matter of fact, it can't do anything. 2 is just 2. 2 is a constant. Okay? So once you've simplified your expression down to just a constant, this limit has no effect on it anymore. Okay, I hope that makes sense. Over here, h was approaching 0, but we had to do some trickery to try and get h out of there so that this whole limit notation wasn't affecting our expression anymore. Okay, so here we just end up with 2. Doesn't matter what the limit is doing, it's a constant value, so that result is 2. Okay, and that's exactly what we expected, right? Since this line has a slope of 2, we expect its derivative at every single point to be 2, because you can think of the derivative as the slope of the function at that given point. So we proved with calculus, something that we already knew, that at x equals 5, the x value equals 5, the slope of my function, which was just a line, is 2. But we know that's the slope everywhere on that function. Okay, so in the next video, we'll move on to not a straight line function. We'll move on to a quadratic function, and we'll show that we can use this formula to find the derivative of that. Okay, I'll see you in that video. Bye.